If reviewing measurements didn't get you excited, I'm sure a review of significant figures will. Again, something that people take for granted, but it is something that we're going to be looking at pretty hardcore when we do any kind of calculations throughout the course. You lose a half point if you don't record your answer with proper units and significant figures, and they'll carry that through on the AP test as well. So we should probably be familiar with some basic sig fig rules. Obviously, these are all the measured numbers plus the estimates. So these are the important or significant figures. All numbers between 1 and 9, all non-zero numbers are significant. And that one usually doesn't cause any major difficulties. It's just that stinking zero. I mean, there's so many different options of where you could find zeros within a number. And that seems to be what causes the most confusion. So here's one option. Leading zeros. Leading zeros are just placeholders. They start off a number. Now, it could be something like this, where it says, 0.00734, or it could be this, 0.00734. I don't know why, but sometimes that zero in the front of the decimal spot causes concern. Either way, this number is really small, so we didn't make a measurement in the ones position. We didn't make a measurement in the tenths or the hundredths. We didn't make a measurement out until the thousandths of a whatever this is, gram, meter, liter. It's something really small. So we want the measured numbers, not these placeholders. So those leading zeros are not significant. Just these last three, the 7, 3, 4. Those are measured numbers. So any zeros that start off a number, whether they're before or after the decimal spot, in the beginning of the number, those are leading and they are not significant. They were not measured. Trapped zeros are zeros, obviously, like within the middle of a number. They're trapped between non-zero numbers. And often these don't cause too much concern. If I have something like 2005. Okay, well, we measured for sure it hit the 2000. It definitely did not hit the 2,100. It did not hit the 2,110. So we're going to estimate, I don't know, maybe 2005, 6. All four of those digits are important. They were measured, the last spot being the estimate, but that is part of the measurement. So all four of those figures are significant. If I have zeros scattered all over the place, I have to combine some of these zero rules. These guys out in front, nope. You're just placeholders. Again, whatever this is, it's really small. I physically did not measure anything in the ones position, the tenths, or the hundredths. I didn't make a measurement until here. But then the 506, those are all measured numbers, the 6 being the estimate. So anytime there's a zero trapped between non-zero numbers, it was a measured zero. Zeros at the end of a number. We need to check for a decimal spot. If the number contains a decimal spot, anywhere in the number, if there is a decimal spot, then that zero at the end was measured. So again, we could have something that's really small. These zeros in the front, these were just placeholders. I did not measure you. There wasn't anything to measure. So, I don't know. I must have some really sophisticated measuring tool here. But I must have been able to measure for sure it hit the 0.002, the 0.0024, and my last spot is the estimate. And if you think it's right smack on the line, you estimate 0, and the estimate is part of your measurement. So a 0 at the end, like this guy, yay, you are part of the measurement. You are the estimate. So these three are significant. The 240. We get something like this 4,000 a lot. And this kind of shows the difference between these last two options. When you have zeros at the end of a number, you want to check for a decimal spot. If the number has a decimal spot, that's our way of saying that, yes, the zeros were measured. This is a possibility. I don't know, maybe I'm measuring some large volume or a large length or something like that. And I know for sure it hits 4,000 milliliters. It for sure does not hit the 4,100. It for sure does not hit the 4,110. And that's the best I can get off my measuring tool. So now I get to estimate the ones. And if I think it's right smack on the line, I'll estimate 0. I think it's right on the line, 4,000. I need to put a decimal spot behind that last 0 to show that all 4 of these are part of the measurement, with the last 0 being my estimate. If I don't put the decimal spot in, if it looks kind of like this guy down at the bottom, 4,000, no decimal spot, this tells me that the number was most likely rounded, which happens. We're going to need to round numbers from time to time. Maybe I'm doing a calculation, or maybe I can estimate in the lab. There are times when we can estimate. It might say get approximately 4,000 grams of something. Well, it might not be exactly 4,000, but maybe that's my estimate. And so the way I'll show that this is not an exact measurement, I don't put a decimal spot in there. Or maybe the original number for some reason was like 4,112. And I was supposed to round to the nearest 1,000. Okay, well then I'll round it to 4,000. But that was not the original measurement, so I will not put a decimal spot to show that this was a rounded number. So these guys, to a rookie, would look the same. It's 4,000. But to us, we are much more sophisticated. We'll say, ooh, those are very different. The first one is much better. I know for sure I can use 4 significant figures in my calculations. This number was measured out to the nearest 10, and then the 1 spot was my estimate. When I don't see the decimal spot at the end, I know the number was rounded. That was not the original measurement. The other one that's kind of sitting in here is a little bit of everything. When you have zeros in the front, these are just placeholders. These are not measured. A 0 trapped between non-zero numbers, you're part of the measurement. And so is that 0 at the end, as long as the number has a decimal spot anywhere in it. So the decimal can be in the front or the back. That's fine. That last 0 again, that was my estimate. Other little sig fig rules that we should be somewhat familiar with. In scientific notation, the significant figures are the numbers that are listed out in front. So if I have 2.0 times 10 to the 4th, the 2.0, there it is, that was measured. Or 5.040 times 10 to the negative 3rd. You don't need to take these numbers out of scientific notation. The significant figures are whatever's listed out in front. You will see quite a few numbers this year in scientific notation. That's a good thing. You don't need to take it out. On the flip side, what if I do something on my calculator and I get this crazy number and, I don't know, it's like, I won't make this too crazy. What if it's like 2,001 point, a bunch of garbage, la 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 la. And so here's the number that I get on my calculator. I plugged a bunch of numbers in. And now for some reason I'm supposed to round this off to like 2 sig figs. Oh. It says like round to, we'll just say like 2 significant figures. And you say, well, I don't know how I can do that, because I mean this number is like 2001. Like, how do I round that off to just 2 significant figures? Throw it in scientific notation. Put it in scientific notation and just leave the first 2 figures out in front. So I could leave this as 2.0 times 10 to the 1, 2, 3. Yeah, I could leave it like that. 2.0 times 10 to the 3rd. Here's 2 significant figures. That will definitely be something that we use, especially after maybe a multiplication. Maybe we're doing like some mole calculations, and as a result of the calculation, we get this giant number, but I need to round it to proper sig figs, and maybe that's less than what I have on my calculator. Scientific notation is probably your best friend in that case. Round it off to the desired amount of figures, and just leave that out in front of the 10 to the whatever power. which kind of brings us into calculations. There are a couple options when you're doing calculations with sig figs. The one that we use most often is this multiplication division rule. You plug it in your calculator, and your calculator will give you a bunch of garbage. We want to round that off to the proper amount of sig figs. Maybe when you were a freshman, they would say, just give me 2 decimal spots. No way, we don't want to do that. We want to look at the data that we have, and we'll record the amount of sig figs that match the least precise piece of data. So for example, if I'm multiplying centimeters, this first number has 4 sig figs. 1, 2, 3, 4. That last 0 counts. That must be the estimate. There's a 0 at the end of the number, and there is a decimal spot in the number. The second one, these leading zeros do not. They are just placeholders. But the 904, those are part of the measurement. So there's 3 significant figures. So I'm going to plug this in my calculator. I'm going to get a bunch of garbage and just write on my calculator. I'm not even going to write all the junk. I'm just going to round this right away to the least amount of sig figs in my data, which is going to be 3. So in my calculator, I only need the first 3 figures, 2.21, and then proper units would be centimeters squared. Easy. Hopefully that rings a bell. Second one, 240 grams. Ooh, there's a 0 at the end. They both have zeros at the end. But that 240 does not have a decimal spot. Tricky. This must be estimated. The 2 and the 4 are significant, but not that 0. If there was a decimal spot at the end, 240 with a decimal spot, then that would be part of the measurement. Then the 0 must have been their estimate. Without a decimal spot, it tells me that this number was rounded. So not the 0. Sorry. But with a decimal spot, this last 0 is the estimate. So this 6.30, they are all significant. So you only have 2 sig figs and you have 3. So I plug this in my calculator. I get a whole bunch of garbage. And I only want to record the first 2 figures. So we could say 38. This must be a density. Grams per milliliter. Yes, I need to record my answers with proper units and significant figures. If you're doing something like this last one, a series of calculations, especially if they're like multiplication and division, which we do very commonly, plug it all in your calculator, and then we'll round it to whatever piece of data has the least amount of sig figs. And again, this should be something that eventually becomes kind of second nature. Like you don't even think about it. I look at my data and really quick I can say, ooh, this guy has 3 sig figs. Trapped 0, yes. This guy has 2 sig figs. A baby could do that. There's no zeros. On this temperature, not the leading 0, but the 9324. So this guy's got 4. I plug this all in my calculator. I'm only going to record the first 2 figures on my calculator, the first 2 digits. I want to go to the least precise piece of data. So we will say this is 8.3, and then my units reflect the calculation. So this is liter times atmosphere over degrees Celsius. We're going to get some kind of funky units throughout the year. It shouldn't be a concern. Just let the unit reflect the calculation. So that was probably the sig fig rule that we use most often. The multiplication division rule. Plug it in your calculator and round to the piece of data that had the least amount of sig figs. The adding and subtracting rule honestly isn't an issue as often, because if you're adding and subtracting data, it's probably like the same kind of data. These are all masses, or maybe we're subtracting final and initial volumes or something like that. Well, realistically, if I'm adding or subtracting volumes or masses, in the lab I probably used the same measuring tool. So I probably have the same amount of decimal spots in all of my data. So when I see something like this where there's different amounts of decimal places, this kind of tells me that they must have used different electronic balances. Or maybe, if it was volume, somebody used different graduated cylinders. Realistically, that doesn't happen as often. But here is the addition subtraction rule. You plug it in your calculator and you round to the piece of data that had the least amount of decimal spots. And it really is decimal spots. It's not sig figs. So you don't have to worry about all those zero rules. I plug this in my calculator. Boom. That's 3 decimal spots. Boom. This is 2 decimal spots. It's only one significant figure, but it's 2 decimal spots. All these zeros count as decimal places. This is 4. I plug it in my calculator. I'm going to round this to 2. 8.11, and it's grams. So not a rule that's as commonly used. Often when we add and subtract, the data is made with the same measuring tool. But if it does happen like this, we go with the number that has the least amount of decimal places.